The third session of the lab is dedicated to analog modulations, in particular to phase and frequency modulations. We'll start with phase modulations, and exercise number 1 is mainly theoretical, just it's about comment the results of the demo file. And in exercise number 2, we will analyze the effect of one of the parameters of a phase modulation, in particular the phase deviation constant Kp. And we are going to vary this parameter. This is going to be pi halves times a constant value z, where this z is going to be modified from 0.1 to 1 in steps of 0.1, just to analyze the effect of this parameter in the signal-to-noise ratio. The result of this experiment is saying that the higher the value of this parameter c, which means the higher the value of the phase deviation constant, the higher the signal-to-noise ratio. Of course, if we include a previous filtering to reduce as much as possible the noise power, we have better results than without this previous filtering. This is obvious. Now, for a fixed value of this parameter, Kp will be equal to pi halves, we are going to obtain the signal-to-noise ratio as a function of the noise power, when the noise standard deviation is increasing from 0.1 to 1 in steps of 0.1. Obviously, the higher the noise power, the lower the signal-to-noise ratio. And again, a previous filtering to reduce the noise power helps to improve the signal-to-noise ratio that we have without this previous filtering. In exercise number 3, a frequency modulation is analyzed. First, the waveform of this modulated signal is plotted, and it is compared with the waveform for a phase modulation signal, with the same type of modulating signal, with a sinusoidal modulating signal. The waveforms of the PM and the FM modulated signals, the phase and frequency modulated signals, is somewhat similar. If they are compared with the carrier, this thin line in red in this picture, the modulated signals sometimes are ahead of the carrier and sometimes are behind of the carrier. The closest at zero are not equispaced as it happens for the carrier frequency, for the carrier. Now, when the frequency deviation constant is modified from 2 Hz to 10 Hz in steps of 2 Hz, the waveform of the frequency modulated signal will be compared with the waveform of the phase modulated signal. Starting from a deviation of 2 Hz, we can see that if we increase to 4, the two signals are a little bit more similar, even more similar for 6, for 8, and for 10 they are a little bit different. This happens because, in fact, the two modulated signals are totally equivalent when the modulation indexes for these two modulations are equal. And this happens for a frequency deviation equal to 7.854 Hz, and it can be seen in this picture over here.